we're going to derive Fresnel's relations. So Fresnel's relations, if you remember in general, give you the reflection coefficient, which is the magnitude of the reflected E field divided by the magnitude of the incoming E field, and the transmission coefficient, which is just the magnitude of the transmitted E field divided by the magnitude of the incoming E field. There are two forms of Fresnel's relations, one for when the electric field is parallel to the plane of incidence, and one for when it's perpendicular. Let's just draw a diagram to make sure we know what we're doing. So here we have the interface. We're going to put in a normal to the interface here. We're going to have an incoming wave here with wave vector k, and it will have an electric field in the first instance like this. The reflected wave will go like this with wave vector k double prime, which has the same magnitude as k but a different direction, and we have the E field like so, E double prime, and then of course we have the transmitted wave with a wave vector k prime and an electric field here, E prime. We have angles alpha, alpha and alpha prime. In this case, the magnetic field is going to be coming directly out of the page, out of the screen towards you. And so in this case, we're looking at the E field is parallel to the plane of incidence. Which means, of course, that the H field is perpendicular to the plane of incidence. This matters because it changes what we do with the boundary conditions. We're going to assume, as usual, that E is a plane wave, so E is equal to E0 e to the I k dot r minus omega t. Generally, we'll assume a linear homogeneous medium, so D is going to equal epsilon E, and we can write omega b is equal to k cross E from Faraday's law, and therefore we can deduce that the H field is equal to the square root of epsilon over mu k hat crossed with E, where we've used the fact that the magnitude of k divided by the magnitude of omega is equal to the square root of epsilon mu, which is one of the phase velocity. So what boundary conditions do we apply? Well, we know that E and H parallel to the plane of the interface are conserved. So notice that this is now slightly different. We're talking about the components parallel to the interface, not the plane of incidence. In the case we've drawn here, where E is parallel to the plane of incidence, H itself will lie entirely in the plane of the interface. So we can say that H0 plus H0 double prime must equal H0 prime at the interface, and that implies that n times E0 plus E0 double prime must equal n prime E0 prime, assuming mu is constant, and generally we assume that mu r is equal to 1. Thinking about components of the E field in parallel to the interface, we can write that E0 cos alpha minus E0 double prime cos alpha must equal E0 prime cos alpha prime. So we now have everything we need. It's just now a case of rearranging. So to find what we call R parallel, we're going to start by writing E0 prime is equal to n over n prime into E0 plus E0 double prime. We've done that simply by rearranging this equation here. And when we do that and we substitute into the second equation, we find the following. We have that E0 minus E0 double prime multiplied by cos alpha is equal to n over n prime into E0 plus E0 double prime cos alpha prime. So we can multiply out and rearrange. We find that E0 into n prime cos alpha minus n cos alpha prime is equal to E0 double prime into n prime cos alpha plus n cos alpha prime, and therefore our parallel, which is just E0 double prime divided by E0, is equal to n prime cos alpha minus n cos alpha prime divided by n prime cos alpha plus n cos alpha prime, and I missed out a prime up there. To find t parallel, we do the opposite. We write E0 double prime is equal to n prime over n E0 prime minus E0. We substitute, we get E0 cos alpha minus n prime over n E0 prime minus E0 cos alpha is equal to E0 prime cos alpha prime. So we're going to multiply the whole equation through by n and then rearrange, and when we do that we find that E0 into n cos alpha, whoops, that's the first term in the left hand side, and then the third term gives us another factor of n cos alpha, and that's going to equal E0 prime into n cos alpha prime plus n prime cos alpha. So t parallel, which is just E0 prime over E0, is given by 2n cos alpha, that's what multiply the E0, divided by n cos alpha prime plus n prime cos alpha. If we want to think about the perpendicular components, so when E0 is perpendicular to the plane of incidence, sorry, not E0, we'll just say that that's E, we only want one underline, so E is perpendicular to the plane of incidence. And remember, the plane of incidence is the plane containing the wave vectors. Then in that case, we have that E0 plus E0 double prime is equal to E0 prime, and we have that H0 cos alpha, minus H0 double prime cos alpha is equal to H0 prime cos alpha prime. That's just resolving the components. That equation there, of course, implies that E0 n cos alpha minus E0 double prime n cos alpha is equal to E0 prime n prime cos alpha prime. So we can rearrange that for E0 prime. So E0 prime is equal to n cos alpha over n prime cos alpha prime into E0 minus E0 double prime. And then we can substitute that back into the equation above. And so we find that E0 plus E0 double prime is equal to n cos alpha over n prime cos alpha prime E0 minus E0 double prime. So we multiply both sides by n prime cos alpha prime, and we gather terms, and when we do that we find that you have E0 double prime into n prime cos alpha prime plus n cos alpha is equal to E0 into n cos alpha minus n prime cos alpha prime. So we've taken the E0 on the left over to the right hand side and the E0 double prime on the right hand side back to the left to get that. So R perpendicular, which is E0 double prime divided by E0, is simply n cos alpha minus n prime cos alpha prime divided by n cos alpha plus n prime cos alpha prime. And to find t perpendicular, we write the following. We have that E0 double prime is equal to E0 minus n prime cos alpha prime over n cos alpha E0 prime. Substituting in again, we find that we have E0 plus E0 minus n prime cos alpha prime over n cos alpha E0 prime is equal to E0 prime. So if we now multiply through by n cos alpha, we find 2 E0 n cos alpha is equal to E0 prime into n cos alpha plus n prime cos alpha prime. So t perpendicular, which is E0 prime over E0, is just equal to 2n cos alpha over n cos alpha plus n prime cos alpha prime. So that completes the derivation of Fresnel's relations. It's important to understand where they come from and to think about and understand how the boundary conditions apply in different directions and to different components. There will be further videos on the special angles, and I will also have a video which includes a Python notebook, a Jupyter notebook, showing values of the Fresnel relations, and also we'll talk a little bit about energy transfer, power transfer, as opposed to simply the coefficients of the fields.